Welcome to the first unit of which is higher level in the topic of thermochemistry, energy cycles. So by the end of the unit, you should be able to use representative equations for enthalpy of hydration, ionization, atomization, affinity, lattice, covalent bonds, and solutions, which we've kind of touched on already earlier in the course. You should know the enthalpy of solution, hydration enthalpy, and lattice enthalpy are related to an energy cycle. You should be able to construct Born-Haber cycles for at least group 1 and 2 oxides and chlorides, construct energy cycles for hydration, lattice and energy solution enthalpy. For example, the dissolution of ammonium chloride or sodium hydroxide in water. Calculate enthalpy changes for Born-Haber or dissolution energy cycles. Relate size and charge of ions to lattice and hydration enthalpies, which again we've probably done already. And perform lab experiments which could include single displacement reactions in aqueous solutions. So what is this? Okay, so let's now look at some key terms. The first one is the standard enthalpy of formation, or delta H naught F. So this standard enthalpy of formation for an ionic compound is the energy required to produce 1 mole of formula units. Remembering, of course, this is the formula unit for sodium chloride, NaCl, the simplest ratio, for atoms in their natural state at 298 Kelvin and 1 times 10 to the 5 pascals. Okay, and that's the example there from sodium chloride. So it's going to be from their atoms, so it'll be 1 sodium and half a diatomic chlorine molecule to give sodium chloride, which gives a certain value. The next one is the enthalpy of atomization, delta H naught at, which is the energy change required to change 1 mole of atoms from their standard state to the gaseous state. So here we have mystery metal mystery metal M going from solid to gas, and it's going to be a lot greater than 0. So the ionization energy, which we've already looked at, the delta H naught IE, is the minimum energy required to remove 1 mole of electrons from 1 mole of atoms or positive ions in the gaseous phase. And these are 2 examples here. And we have already looked at that in our second unit. Then we have the electron affinity, delta H naught EA, which is the energy change that occurs when 1 mole of electrons joins to 1 mole of atoms in the gaseous phase. Okay, we've already looked at this previously when we looked at periodicity, but it's basically mystery element X in a gaseous phase gaining an electron to become the associated ion. Then we have lattice enthalpy, delta H naught lattice, which is the energy required to convert 1 mole of solid compound into gaseous ions. Okay, so we've got mystery compound MX, and it's going to then basically be turned into the corresponding ions in the gaseous phase. So for example, sodium chloride being converted into sodium ions and chloride ions, which has a lattice energy of plus 771 kilojoules per mole. So the magnitude or size of this lattice enthalpy depends on 2 things, which we've already kind of looked at when we looked at periodicity, but it depends on the size of the charge of the ion. So the greater the charge of the on the ions, the greater the attraction electrostatically, thus the greater the lattice energy. So that means that 2 plus, of course, is going to have a larger attraction than an ion with 1 plus. So that means magnesium oxide, for example, has a larger lattice enthalpy than sodium chloride. So also the size of the ions is important. So the larger the ions, the further apart they are. So that means it's going to be a reduced lattice energy, okay, because there's less electrostatic attraction. So there's some examples here. So sodium chloride, reasonably large lattice energy enthalpy, okay, of minus 780. So plus 1 charge plus minus 1 charge. Okay, but then as we increase to a minus 2 charge for the oxygen, you'll notice that the enthalpy balloons out to minus 2,478. Okay, the same you can see there also for potassium. Okay, and you'll notice, of course, that magnesium 2 plus, larger charge, so 2,256. And you'll also notice the difference between sodium and potassium, because potassium is a larger ion it's going to have a reduced lattice enthalpy because of the larger distance between the ions. Okay. Smaller ions will have the greater attraction to each other because of their higher electron density. They will have larger lattice enthalpies and larger melting points because of the extra energy which must be put out, okay, to separate the oppositely charged ions. Kind of makes sense, and kind of reinforcing the stuff we looked at when we looked at periodicity. So here's just illustrating that further. The sodium ion has the same charge as the potassium ion, but is smaller. It has a higher charge density, so will have more effective attraction to the chloride ion. More energy will be released when they come together. Okay, that's just basically illustrating the size of the ion, which is illustrated by the numbers in the previous slide, is a determining factor for lattice enthalpy. So now let's introduce the concept of the Born-Haber cycle. So what is a Born-Haber cycle? Well, the Born-Haber cycle is a diagrammatic representation of the formation of ionic compounds, starting from the associated atoms, moving into the gaseous atoms to the gaseous ions to form a solid compound. And we use it to determine this lattice enthalpy, which we've already touched on. Okay, so you can basically see it's kind of like an extension of Hess's law. We're just basically adding up all these different enthalpies to get the enthalpy or formation of a solid compound. Okay. So here's the Born-Haber cycle for sodium chloride. So the first thing you get is that you have obviously sodium atoms and chlorine atoms, okay, and we want to atomize them. Okay, so it goes from having 0 energy to about 107 kilojoules per mole. Okay, so what we've done is we've moved the sodium into the gaseous phase, okay, from being solid to gas. Then we wish to atomize the chlorine, just as we've done with the solid, okay, and that requires 121 kilojoules per mole. Okay, so we've gone from sodium solid to sodium gas, and now we've gone from chlorine diatomic, okay, to chlorine atom in the gaseous phase, and that's now up to about 220 kilojoules per mole. Then we introduce the idea of the first ionization because we want to form ions. Okay, so we will now form the sodium ion from the sodium atom in the gaseous phase, and this requires 502 kilojoules per mole. So now we're up to about 720 roughly kilojoules of mole of energy because now we've formed the sodium ion. And then we also have to consider the electron affinity of chlorine, okay, because now basically we've got this electron has been removed to form the sodium ion, so it requires energy therefore for the chlorine atom in the gaseous phase to gain the electron to become the chloride ion, and that's minus 355 kilojoules per mole. So we're just adding all these numbers together. Okay, so now it's around about 370 kilojoules per mole. And then we have finally the formation of sodium chloride. So the sodium ion and the chloride ion therefore interact to form the sodium chloride lattice, and that's in total the number that we've ended up with, minus 411 kilojoules per mole. Okay, so that's the delta H formation of the sodium chloride. Okay, and finally we have the lattice enthalpy of the sodium chloride, which will be the difference between this number and this number, which is 786 kilojoules per mole. So essentially that's applying Hess's law to Born-Haber cycles. Okay, so you're essentially rearranging to find the lattice energy. Okay, so delta H formation will equal the delta H atom of sodium plus the delta H atom of chlorine atomization, plus the delta H ionization energy, plus the delta H electron affinity, minus the delta H lattice, which will give you the delta H formation. You rearrange the equation to find the delta H lattice, which is the following equation there. So in terms of the experimental and theoretical calculations, there is a bit of a difference, and the difference is accounted usually because of the covalent character increasing down a group and across a period. Okay, so covalent character increases as the difference between the experimental and theoretical values of lattice enthalpy increases. Okay, so essentially you can see that the salts of silver have more of a covalent character than the salts of sodium. Okay, essentially due to its electronegativity of sodium being a lot lower than silver. And you can see that the discrepancy especially is more marked in silver as you go down the group between fluorine, chlorine, and bromine, and, well, iodide really, isn't it? So fluoride, chloride, bromide, and iodide, going from 9% discrepancy to about 16%. So solvation, or making solutions, is when intermolecular forces form between a solvent, say water, and the solute sodium ions. And the type of ion formed affects the strength of the bond, as you can see there. So the strength is obviously a lot stronger with aluminium compared to lithium. Kind of makes sense because aluminium is a 3+ charge, so more attraction between the solvent and the solute. So the enthalpy of solution is the energy change that occurs when 1 mole of substance dissolves in excess of solvent. And its value can be either positive or negative. So here we have a salt dissolving into the corresponding ions. And the enthalpy of hydration is the energy change that occurs when 1 mole of a gaseous ion is added to water to form a dilute solution. This value is always negative. If another solvent other than water is used, it is the enthalpy of solvation. So enthalpy of hydration only corresponds to water. Okay, so just to finish off, calculate the enthalpy of solution for sodium hydroxide using your data booklet, and given the latest enthalpy of sodium hydroxide is 900 kilojoules per mole. So pause the video now and see if you can find the answer for yourself. So welcome back. So what's the first thing we have to do? Well, first thing is we have to write down the equation. So what are we doing? We're saying, well, sodium ions plus hydroxide ions will give a lattice energy of plus 900 kilojoules per mole. So we're basically, that's what the lattice enthalpy is told, okay? And that the delta H naught of hydration is going to be negative 424 plus negative 519 kilojoules per mole, which we've got from our data booklet for sodium ions and chloride ions. Okay, so that's basically sodium ions plus hydroxide ions aqueous. So the delta H naught of solution of sodium hydroxide, therefore, will be the following. Okay, it will be the delta H naught lattice of sodium hydroxide plus the delta H hydration of sodium ions plus the delta H naught of hydration of hydroxide ions, just like in Hess's law. It will be 900 plus negative 424 plus negative 519, which will give negative 43 kilojoules per mole. An exothermic process. Okay, which is what you actually feel if you add sodium hydroxide to water. Then what happens is that it feels hot. Okay, so that's pretty much all we need to know for lots of definitions to remember, but that's all we need to really know for the associated Born-Haber cycles.